In Chapter 13, we will focus on a very important type of distribution that applies to quantitative data, called the normal distribution. These are the concepts we will discuss in Chapter 13. Density curves, center and spread of a density curve, the 68, 95, 99.7 rule, and then finally percentiles of normal distributions. We now have several tools for analyzing quantitative data. We'll usually begin with a graph, either a histogram or a stem plot. This will give us a sense as to the shape, center, and spread of our data set. If the data set is symmetric, then we can use the mean and standard deviation to describe the center and spread. If the data set is skewed or has outliers, we can use the 5-number summary. As we'll see in this chapter, we can describe the shape of a distribution by a smooth curve if the data set is large by mimicking the shape of a histogram. For instance, let's consider the two histograms below. In both cases, a smooth curve is superimposed that approximates the shape of the histogram. Both curves are examples of what we'll call densities. Notice how the area of each rectangle is approximately equal to the area under the curve between the edges of each rectangle. Like we said, a density is a curve that has approximately the same shape as a histogram. If we set our scale so that the area of each rectangle is equal to the proportion of the observations that fall into each class, then this area should be approximately equal to the area under the density curve. For this to be true, we must ensure that the total area under the density is exactly 1. A good way to think about the relationship between a histogram and a density is through the relationship between a sample and a population. In particular, histograms are computed using data from a sample, whereas the density describes the distribution for the entire population. Furthermore, as the sample size increases, the closer the shape of the resulting histogram and density will be. Let's look at an example. Figure 13.4 copies Figure 13.3, showing the histogram and the density curve that describe this dataset of 1,000 sample proportions. What proportion of the observations are greater than 0.51? From the actual 1,000 observations, we can count that 171 are greater than 0.51. So the proportion is 171 over 1,000, or 0.171. Now, because 0.51 is one of the breakpoints between the classes in the histogram, the area of the shaded bars in Figure 13.4a makes up 0.171 of the total area of all the bars. Now concentrate on the density curve drawn through the histogram. The total area under this curve is 1, and the shaded area in Figure 13.4b represents the proportion of observations that are greater than 0.51. This area is 0.1667. You can see that the density curve is a quite good approximation. Density curves help us better understand our measures of center and spread. Areas under a density curve represent proportions of the total number of observations. In particular, the median is the point with half the observations on either side. So the median of a density curve is the equal areas point, the point with half the area under the curve to the left and the remaining half of the area to the right. The quartiles divide the area under the curve into quarters. 1/4 of the area under the curve is to the left of the first quartile, and 3/4 of the area is to the left of the third quartile. You can roughly locate the median and quartiles of any density curve by dividing the area under the curve into 4 equal parts. If we think of the observations as weights stacked on a seesaw, the mean is the point at which the seesaw would balance. This fact is also true of density curves. The mean is the point at which the curve would balance if made of solid material. A symmetric curve balances at its center because the two sides are identical. The mean and median of a symmetric density curve are equal. However, we know that the mean of a skewed distribution is pulled toward the long tail. So let's summarize some of the items from the last 2 slides. The median of a density curve is the equal areas point, the point that divides the area under the curve in half. The mean of a density curve is the balance point, or center of gravity, the point at which the curve would balance if made of a solid material. The median and mean are the same for a symmetric density curve. They both lie at the center of the curve, like in figure A. The mean of a skewed curve is pulled away from the median in the direction of the long tail, like in figure B. For instance, in figure B, our distribution is skewed to the right, which means that our mean will be pulled towards the right tail. So let's talk about a very important, very special type of density curve called a normal curve. Normal curves are symmetric, single-peaked, and bell-shaped. Their tails fall off quickly so that we do not expect outliers. Because normal distributions are symmetric, the mean and median lie together at the peak and the center of the curve. Normal curves have the special property that giving the mean and standard deviation completely specifies the curve. The mean fixes the center of the curve, and the standard deviation determines its shape. Now, changing the mean of a normal distribution does not change its shape, only its location on the axis. Changing the standard deviation does change the shape of a normal curve. In particular, the larger the standard deviation, the wider the curve will be. So for instance, in the 2 normal curves above, the one on the left has a much larger standard deviation. Here is a summary of basic facts about normal curves. Normal curves are symmetric, bell-shaped curves that have these properties. A specific normal curve is completely described by giving its mean and its standard deviation. The mean determines the center of the distribution. It is located at the center of symmetry of the curve. The standard deviation determines the shape of the curve. It is the distance from the mean to the change of curvature points on either side. There are many normal curves, and each is described by its mean and standard deviation. All normal curves share many properties. In particular, the standard deviation is the natural unit of measurement for normal distributions. This fact is reflected in the following rule, called the 68-95-99.7 rule. In any normal distribution, approximately 68% of the observations fall within 1 standard deviation of the mean. 95% of the observations fall within 2 standard deviations of the mean, and 99.7% of the observations fall within 3 standard deviations of the mean. Furthermore, the remaining 0.3% of the observations are more than 3 standard deviations away from the mean. Let's look at a figure to visualize the 68-95-99.7 rule. Here we have an example of a normal curve whose mean is 0 and whose standard deviation is 1. This is also called a standard normal curve. According to the rule from the previous slide, 68% of the observations are within 1 standard deviation of the mean. 95% are within 2 standard deviations of the mean, and 99.7% of the observations are within 3. Like we said, the remaining 0.3% of the data are more than 3 standard deviations from the mean. Let's do an example where we apply the 68, 95, 99.7 rule. The distribution of Iowa Test of Basic Skills vocabulary scores for 7th grade students in Gary, Indiana is normal with mean 6.84 and standard deviation 1.55. Let's sketch the normal density curve for this distribution, and then we'll answer a few questions about it afterwards. So first, the distribution is normal, so we have a bell curve. We have a peak at the mean of 6.84. If we add and subtract 1.55 from 6.84, we will see the range of values for which 68% of the observations lie. This is the range of values that are within 1 standard deviation of the mean. If we add and subtract 2 times 1.55, or 3.10 from 6.84, we will see the range of values for which 95% of the observations lie. This is the range of values that are within 2 standard deviations of the mean. Similarly, 99.7% of the observations are between 2.19 and 11.49. So, what percent of the ITBS vocabulary scores are less than 3.74? Now 3.74 is 2 standard deviations below the mean. We know that about 95% of the observations are within 2 standard deviations of the mean, so about 5% of the observations are outside this range. Furthermore, because of the symmetry of the normal curve, about half of these values will be more than 2 standard deviations below the mean, and about half of them will be 2 standard deviations above. Putting this all together shows that about 2.5% of the scores are less than 3.74. Finally, what percent of the scores are between 5.29 and 9.94? First, 5.29 is 1 standard deviation below the mean, and 9.94 is 2 standard deviations above the mean. We want to find the area between these two values. We'll do this by adding the area between 5.29 and 8.39 to the area between 8.39 and 9.94. The area between 5.29 and 8.39 is about 0.68 or 68%, because this is the range that is within 1 standard deviation. To find the area between 8.39 and 9.94, we recognize that 95% minus 68%, which is 27% of the observations, are more than 1 standard deviation, but less than 2 standard deviations from the mean. Finally, by symmetry, half of these observations are between 8.39 and 9.94, so 13.5% are between these values. So, adding 68 to 13.5 gives us a final answer of 81.5%. Like we said previously, a normal distribution is completely determined by its mean and standard deviation. To compare observations from different distributions, we can use a process called standardizing. By definition, the standard score for an observation is equal to the value of the observation minus the mean divided by the standard deviation. The standard score tells us how many standard deviations a particular observation is above or below the mean. Let's look at an example. Jenny scored 600 on the SAT mathematics exam. Her friend Gerald took the ACT test and scored 21 on the math part. ACT scores are normally distributed with a mean of 18 and a standard deviation of 6. Although it's not listed here, the SAT Mathematics exam is also normally distributed with a mean of 500 and a standard deviation of 100. If we assume that these tests measure the same kind of ability, then who has the higher score? We'll answer this question by comparing the student's standard score. So Jenny's standard score is 1.0. This is found by taking her score, 600, subtracting off the mean, which is 500, and then dividing by the standard deviation, which is 100. Jenny's score is exactly one standard deviation above the mean. For Gerald's standard score, we get a value of 0.5. This again is found by taking Gerald's score minus the mean divided by the standard deviation. Because Jenny's score is one standard deviation above the mean, and Gerald's is only 0.5 standard deviations above the mean, Jenny's performance is better. Standard scores allow us to quickly relate an observation to others in the distribution. In particular, we can use them to describe what percentage of the observations lie above and below it. This brings us to the idea of a percentile. The cth percentile of a distribution is a value such that c% of the observations lie below it and the rest lie above. The median of any distribution is the 50th percentile, and the quartiles are the 25th and 75th percentiles. In any normal distribution, the 0.1 standard deviation above the mean is the 84th percentile. Every standard score for a normal distribution translates into a specific percentile, which is the same no matter what the mean and standard deviation of the original normal distribution are. Table B at the back of this book gives the percentiles corresponding to various standard scores. So for example, what is the percentile corresponding to the standard score of 1.0? If we look up 1.0 in the standard score column, we see the percentile is 84.13. How do we interpret these values? So 84.13% of the observations are less than one standard deviation above the mean. Furthermore, the remaining 15.87% are more than one standard deviation above the mean.